just been doing homogeneous, linear, second order differential equations. What about nth order differential equations? Arbitrary order, we can go higher and higher. Actually, in practice, anything beyond about fourth order is not very useful. It's very seldom there's any physical application. But we do take an interest in third and fourth order equations, and the theory of high order equations follows beautifully from what we do in the third and fourth order equations. So we want to talk about them all today. And the good news is that they're sort of similar to what we did for second order. So here's an nth order homogeneous linear equation that looks like this. Function of t only times nth derivative plus a function of t only times n minus 1 derivative all the way down to a function of t only times y itself equals 0. These have some interesting theory involved, and one of them is you start off with the same kind of thing. You say, suppose I have a bunch of linearly independent solutions. How do I tell if they're linearly independent? We'll say, first of all, that a set y1 through yn form of functions form a linearly independent set on an interval I, your solution interval, of n times differentiable functions, right? They have to have an nth derivative. If there's no linear combination of them, let me shrink this down just a little bit so you can see the whole thing. If there's no linear combination of them, c1 y1 plus c2 y2 plus dot 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 cn yn, we take a constant times one plus a constant times another all the way through a constant times the last one. We call that a linear combination of the n functions. If no linear combination makes those functions 0 on the whole interval unless all the constants are 0. That's the definition of linear independence. If you've taken linear algebra before, that probably sounds perfectly familiar, and otherwise it probably sounds very abstract. And then otherwise they're linearly dependent. But it's like what we did for two equations. It's just now that linear dependence is not so simple. Before, two functions were linearly independent. If one was a multiple of the other. This is not so simple. It might be that you add a multiple of one and a multiple of another and get that equal to the third one. So one might be equal to linear combination of some of the others. But how do you tell when it's so hard to tell? It's not just one is a multiple of the other anymore. Well, here's how you can tell. There's a bigger Wronski. You put y1 through yn, all functions of t, in the first row of a matrix, a big old matrix. Then you put their first derivatives in the second row. This dot here means derivative with respect to t. It's another notation, so you can also put prime here. But sometimes when these are functions of t, we'll use dot instead. And then all the way down to n minus first derivative in the last row. Zeroth derivative through n minus first derivative into a big matrix, and then these straight bars on the side mean determinant. In calculus, you saw determinants of 2 by 2 and 3 by 3 matrices. N by n matrices have a similar formulation to what you did with 3 by 3 matrices. We aren't going to do those. I'm not going to ask you to show that more than 3 functions are linearly independent. When you take matrix algebra, if you take that, you can see how to do larger matrices. But we'll just try some 3 by 3 matrices and say, show these are independent. And actually, the computation for the bigger matrices actually gets to be quite complicated also. It gets to be a long process. All right. So the determinant of these, just remembering what you did for 2 by 2 and 3 by 3 determinants from calculus, can tell you whether the functions are independent or dependent. And Abel's theorem extends to these for the special case that the functions you put in here are solutions of a linear equation in standard form. You divide through by the lead coefficient. With continuous coefficients, either the determinant will be, the Wronski will be 0 on the whole interval, and they'll be dependent, or it'll be non-zero on the whole interval, and they'll be independent. So it's very nice. For other functions that aren't solutions of such an equation, it's not so simple. In fact, the Wronski can be 0 and the function still be independent. But it is the case for general functions in here that have n-1 derivatives, that if the Wronskian is non-zero at some point in the interval, then they're independent. So you can do that with general functions. Again, we won't worry about that for this section. We'll simply say, suppose they're actually solutions of this differential equation divided through by a n of t, so it's in standard form. If all those are continuous in a homogeneous linear equation, then you can just test the Wronskian at one point. If it's not zero, then it'll be not zero in the whole solution interval, and the solutions will be independent of the interval. That's what we need to know. So, suppose I want to determine whether a set of solutions of this differential equation, y triple prime plus y equals 0. Here's three solutions: cosine t, sine of t plus pi over 4. Is that a linearly independent set on minus infinity to infinity? Let's see. We put them into this 3 by 3 Wronskian, cosine, sine, and sine of t plus pi over 4. Well, they look kind of the same. Maybe they're dependent. I don't know. What happens is if you take their derivatives, derivative of cosine is minus the sine, derivative of the sine is the cosine, derivative of sine t plus pi over 4 is cosine t plus pi over 4. Then you take the derivative again in the same fashion via calculus. If you look at it, the third row is actually just minus the first row. And so if you compute the determinant with 3 by 3, remember how to do these determinants. It takes this one times this subdeterminant minus this one times the subdeterminant gotten by wiping out its row and column, plus this one times the subdeterminant gotten by wiping out its row and column. Maybe we should write that down later in a little bit. But it's out of calculus and also out of linear algebra. But whenever you notice one row is a multiple of another row, or any linear combination of the other two rows, you instantly know that the determinant is 0. So this determinant, this Wronskian, is going to be 0, and therefore these three functions are a linearly dependent set. We also have this nice result that if you have a set of solutions, any linear combination of them is also a solution. So that's, the proof is analogous to the proof that we did last time for second order equations. You just do exactly the same proof with nth order equations and m-independent solutions, and you can show that a linear combination of a multiple of one plus a multiple of another plus dot 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 a multiple of another is a solution whenever the individual functions are solutions. Here it is. So you just put y equals this linear combination of m functions in, and you say the derivative of the sum is the sum of the derivatives like this, and then you pull the constants out and you regroup them like this, and then if y1 is a solution, then this is 0 because that was the differential equation is this equals 0. If ym was a solution, then this is 0 because this equals 0 was the differential equation. So you add up all the zeros and you get 0. Sure enough, this will be a solution if each of the y1 through yn was. Alright, and then a big theorem. This is a pretty amazing fact, really. And we're not going to prove it. The proof is extraordinarily detailed. If you're interested, I can point you to a book, Nagel et Saf, Differential Equation and Boundary Value Problems, I think it's called. There's a little bit more to the title. But I have a copy if you want to look it up. In the appendix, they put it back there. It's a long proof. Any n linearly independent solutions, y1 of t through yn of t, of a homogeneous nth order linear differential equation with continuous coefficients not equal to 0 on an interval I, independent, form a fundamental solution set, we call it, in the sense that the general solution, the form of all solutions, can be written as an arbitrary linear combination of the n solutions. So not only if you get n solutions to an nth order equation, is any expression of this form a solution. If y1 through yn are also independent, then this is the form of all solutions. How about that? You can write every solution once you get n independent solutions. That's why we went through all this worry about are these independent, just because if we know that if they're independent, we can write the general solution in terms of them, where C1 through Cn are arbitrary constants. Here's the most important case. This is the one we really want to look at because it's the one that comes up the most in practice. Suppose you have constant coefficients. A0 through An are actually just numbers, not functions of t in particular, but just plain old numbers. In this case, we can do the same thing we did with second order equations. We can say, let's try substituting in a trial solution y equals e to the r2, e to the rt, and maybe we'll come up with some of these as solutions. And so we plug it in full of hope, and the first derivative of e to the rt is r e to the rt. The second derivative is r squared e to the rt, remember from last time. And the nth derivative of e to the rt is r to the n e to the rt. So the nth derivative here gets replaced by r to the n e to the rt, multiplied by n. N minus first derivative is r to the n minus 1 e to the rt, that multiplies the n minus 2, and so on. Just by plugging in e to the rt and its derivatives, we get this equation. Now you can divide through by e to the rt, because after all it is a 0, right? E to the anything is a 0. And we get this polynomial equation that's called the characteristic equation for the nth order differential equation. It should sound just like last time, just for nth order equations in general, n equals 1, 2, 3, 4, 5, on forever, instead of just second order equations that we did last time. So every nth order homogeneous linear equation with constant coefficients, quite a mouthful, isn't it? Has a characteristic equation that is just an nth degree polynomial, right? Remember these polynomials from algebra? A number times the whole power of r plus a number times the whole power of r plus dot dot dot. I forgot my dot 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 in here. Plus a number is called a polynomial, and now I have an nth order polynomial equation for the characteristic equation instead of a second order polynomial equation. Now, from this, we can always, it turns out, deduce n linearly independent solutions and therefore get the general solution of the differential equation. So how do we do it? We just need to find these r values that satisfy an nth order polynomial. Maybe there's an nth degree polynomial equals 0 solution, just like there's a quadratic equation, right? A quadratic, if this was second order, you'd call this a quadratic equation. And there's a quadratic formula that always solves it. If there's complex solutions, you find what they are. You get two complex conjugates. Or you can get two real solutions that are distinct, or two real solutions that are equal. There's only 3 cases. Maybe we can get so lucky and find out that in fact nth order polynomials have the same trick. And alas, they don't. Here's the situation. I'll just remind you, if you had a first degree equation you were solving, a dy dt plus b y equals 0. This is a first order linear homogeneous equation with constant coefficients, a and b, right? Constant. It has characteristic equation ar plus b equals 0, and ar plus b equals 0 has exactly one solution, r equals minus b over a, and you can always solve it, and what's more, it's real. If you have one that's a d squared y dt squared plus b dy dt plus c y equals 0, this is a homogeneous linear second order differential equation with constant coefficients. This one, we said its characteristic equation is ar squared plus br plus c equals 0. I'm not going off the screen there. But it's a quadratic equation. And you can always solve this with the quadratic formula. So a linear equation you can always solve just by subtracting b and dividing by a. A quadratic equation can always be solved by the quadratic formula. Wouldn't it be nice if there's a higher order equation for higher degree polynomials? By the way, it's called a quadratic equation because this is a second degree polynomial. Is called a quadratic polynomial or a quadratic function. So a quadratic polynomial equals 0 is a quadratic equation. Linear polynomial equals 0 is a linear equation. We can have a cubic equation. That's a third degree polynomial equals 0. Or quartic equation. Fourth degree polynomial equals 0. Quintic and so forth. And it turns out there is a cubic formula. We can write it down, but it's kind of complicated. Hardly anybody memorizes. I don't remember it. And it's a mess. Nobody wants to use it if they don't have to. But it is there, and machines can do it pretty well. You can go out on Symbol Lab or one of those places and solve your third degree polynomial characteristic equation you get here. And so you can solve third degree equations that way. In fourth degree equations, there's a quartic equation that can always be solved. It involves fourth roots, and the cubic equation involves third roots. And there's a nice algebraic equation formula by which you can solve any polynomial equation through fourth degree. And then, alas, at the very end, after fourth degree, no more formula. It's kind of a fascinating result, but there is a finite algebraic formula, a quadratic formula for second degree polynomials, right? R equals minus d plus or minus square root b squared minus 4ac all over 2a. So there's a finite algebraic formula, meaning in terms of arithmetic powers and roots. And there's one for first degree polynomials, and third and fourth. But fifth degree and higher, amazingly, you can prove it comes out of Galois theory. There is no finite algebraic formula for n greater than or equal to 5 polynomials. Isn't that strange? It's like asking, why is space-time four-dimensional? Maybe it has something to do with this. Probably not, but it's a neat idea. But there is no finite formula for n greater than or equal to 5 polynomial equals 0. All hope is not lost, because a lot of times you can kind of guess, depending on what these numbers are. Remember the rational zeros formula or rational roots formula theorem is called both. If these are, say, whole numbers, well, say integers, numbers with nothing after the decimal point, then you can try and guess some fractions, some rational numbers that might be solutions. And it's always plus or minus a factor of a0, the constant term, over a factor of an, the coefficient of the dominant in the dominant term. And if there are any fractions, this will get all of them. You just plug them in and try them, and if they make this equal to 0, then you got a solution. And then once you've got one of those, you can take x minus that number and divide this through and reduce the degree of the polynomial and find the ones that are irrational, that can't be written as fractions. Right. Rational numbers are the ones that can be written as ratios, fractions, ratios of integers to integers. So if it's 50 degree or higher, don't give up. You might be able to guess one of them, and then you can reduce the degree of the polynomial by polynomial division and get the others. And sometimes they're just so obvious, or sometimes people give you these already factored. So, by the way, I should mention Galois here has an interesting story while we're at it. It's time to wake up for a while. I was running out about this time in the lecture. Here it is from Wikipedia. Maurice Galois was a guy about your age. He died when he was 20. It was the time of the French Revolution, and he got out in a duel over a girl and got himself shish kebab and died the next day. But before he died, he was brilliant. People think he would have been a great mathematician. It's too bad he died. You can read on there, he was able to determine a necessary and sufficient condition for a polynomial to be solvable by radicals, like we've been writing with the quadratic formula for second degree polynomials, thereby solving a problem standing for 350 years. His work laid the foundations for Galois theory that we study in graduate school now, in group theory. And so he sort of got the foundations going of that. And one of the results of Galois theory is that there is no finite formula for polynomials, polynomial zeros of fifth degree and higher, as we are discussing. So you can go through and look all about it if you take any interest in that. Let's see. All right, and now let me get back to what I was working on here. So his theory is the reason we have so many troubles here is we know we can't do these higher order things, but we can try and use the method of lucky guessing. And actually numerical methods can estimate all the solutions to these higher degree polynomials. They can't get them exactly, but they can number crunch to as many digits as you want for most of these higher degree polynomials. Maybe if you took a millionth order one, it'd have a hard time, I don't know, but they can find polynomial zeros very effectively if you just want a decimal approximation. And then, now what do we do for the ones we can't solve? Algebra. You should remember from algebra that for a polynomial of degree n greater than or equal to 1, there's this nice theorem that this left side, called a polynomial, factors uniquely, every polynomial factors uniquely as a constant in front times, if you want, the product of linear factors, a number times x plus a number, I should have said number times r plus a number, that's called a linear polynomial, and irreducible quadratic factors, second degree polynomials, ar squared plus br plus c. And so there is actually a unique way to factor it down to first and second degree things. Once it's first and second degree, use the theory we used from second order equations and solve these the same way. So up to reordering the factors, you can multiply them in any order, obviously. What's an irreducible quadratic? An irreducible quadratic is one of these that doesn't factor any further using the real numbers because b squared minus 4ac is less than 0. All right, and if b squared minus 4ac is greater than 0, then you find the solutions to the quadratic formula, and the lead coefficient times r minus the first solution times r minus the second solution is how it factors. But if these two are complex, then it factors the complex numbers, and those are hard to guess. But you need to use the quadratic formula to get them. So that's what we'll do on these higher degree polynomials. We will factor them into linear factors and irreducible quadratics, and then the irreducible quadratics we can solve for the zeros of those using the quadratic formula, and thereby we can get from an nth degree polynomial n different values of r, and deduce from those, it turns out, n independent solutions, and always solve these equations, provided we can get past the Galois conundrum that we can't necessarily find all the r's. But when we can find them, we can always find all the solutions. That's the point. All right, and frequently we can find them all. All right, here's the meat of the discussion here. This pulls it all together, but it's very dense, right? There's a lot of stuff in here. For each repeated real solution of multiplicity m, all right, if you solve the characteristic equation, you get R1, R2, R3, Rm all equal. You might get a bunch of them equal. These are the solutions. E to the RT is a solution by what we did just plugging in the test solution. We proved it. But then if you plug it in, you'll find out that T e to the RT, whatever r it is also a solution. T squared times that is T cubed is all the way up to Tm minus 1 if it's a factor, if it's a solution multiplicity m of the characteristic equation. You can come up with m independent, you can put them in the Wronskian and C, solutions, e to the RT, T e to the RT, and T all the way to Tm minus 1 e to the RT are all independent solutions. For each, this is waxing abstract here, so we'll get a concrete example in just a second. And then you can get complex conjugate pairs of solutions. If Rk and Rk plus 1 are two complex conjugates, right? A real number plus I times another real number, and that are solutions of the characteristic equation, then these are linearly independent solutions by the proof again above, just like they were before, and you can take the sum of them over 2 and get e to the alpha t cosine beta t, and you can take their difference over 2I and get e to the alpha t sine beta t, just like we did last time for the first pair. But what if you get a repeating pair of complex conjugates? Now you might have a fourth degree polynomial and two pairs that are equal. Well, in that case, then you have to just take multiples of t times these. You can take t times this one and t times this one for the second pair, and t squared times this one and t squared times this one for the third pair, and so on. But the point is, you do that until you get one for each repeating R here, and you can come up between these two things with always n independent solutions that are either exponentials times powers of t, or exponentials times sines, exponentials times cosine times powers of t, and solve the differential equation. We aren't going to do anything beyond fourth order here, but I wanted you to see the general theory. So here's a good example. Suppose I want to solve this third order differential equation, d cubed y dt cubed plus 6d squared y dt squared plus 12d y dt plus 8y equals 0. The corresponding characteristic equation is r cubed replacing the third derivative, r squared replacing the second, r replacing the first, and 1 replacing y itself. And this then is the characteristic equation that goes with this differential equation. Now, we don't have a quadratic formula because it's a third degree polynomial, so I have to try and guess a factor, and I might think, well, every rational zero, if there are any, has to be a factor of 8 divided by a factor of 1. Right? So it's plus or minus 8 over 1 would be a pair of factors. What if I try plugging in 8? 8 cubed plus, oh boy, 6 times 8 squared. 8 cubed is so big, these are never going to get it back to 0, so it can't be 8. Maybe I'll try a factor of 8 over is 1 over a factor of 1 is 1. So maybe let's try plugging in 1. 1 cubed plus 6 plus 12 plus 8. Wait a minute, these are all positive. That's not going to work. R has to be negative. So you do things like that. Let's try a negative 2. That's not so big as 8 that this overwhelms everything. And it's negative, so maybe I can make these add up to 0. Minus 2 cubed is minus 8, plus 6 times minus 2 squared is plus 24, makes 16. Minus 24 plus 8, sure enough, it's 0. R1 equals negative 2 is a solution to the characteristic equation, which tells me that e to the minus 2t is in fact a solution to the differential equation. So y1 of t equals e to the minus 2t. Since r1 is a 0 of the characteristic equation, now I know e to the r1t is a solution to the differential equation that it came from. But how do I get the other zeros? Once you find one of these, you're home, because right now you remember polynomial division from algebra. You can also do synthetic division when it's just r minus a number like this, or when r. You can also use synthetic division. It's faster, but hardly anybody remembers it. I'll do long division here. If r1 equals negative 2 is a 0 of the polynomial, right, then remember that r minus that number is a factor. So r plus 2 is a factor. I'll divide r plus 2 into this polynomial and reduce its order, then I'll be able to find the other zeros. So r plus 2, I need to get an r cubed, so I'm going to have to multiply by r squared. R squared times r is r cubed, and then I've got plus 2r squared here, right? And I subtract down, these subtract down to 4r squared, and then I'm carrying on still to 12r plus 8. Now to get 4r squared, I'm going to have to multiply r by 4r. 4r times r is 4r squared as I wanted. 4r times 2 is 8r. And now I subtract those down, and these cancel, and I get 12 minus 8r is 4r plus 8. To get that, I can add 4. All right, 4 times r gives the 4r. 4 times 2 gives 8, and these subtract out and give me 0. Sure enough, r plus 2 divides r cubed plus 6r squared plus 12r plus 8 with quotient r squared plus 4r plus 4. This says that the original polynomial equation can be written as r plus 2, the factor we figured out by plugging in minus 2, times the rest of this, r squared plus 4r plus 4. See, you thought you'd never use your algebra when you took that class probably. So it factors that far. How do I find the rest of this? Well, remember the quadratic formula though. The quadratic formula for this one says R2 and R3, we can call it zeros. R2 and R3 come out to be, or you can factor it, maybe guess the factors. This factors as R plus 2 times R plus 2, or you can use the quadratic formula and you get R is negative 2 and negative 2 by the quadratic formula. Either way, this whole thing factors as R plus 2 times R plus 2 times R plus 2 equals 0. That says R1, R2, and R3 are all equal to negative 2. The three solutions. We'll put it right off the edge there, but you heard it anyway. Which means this is one solution, but the other two, y2 of t, is not independent. When it's not independent, what did you do for second order equations? You multiply by t, and this turns out to be a solution. You can plug it in and see, but once you know what it is, you don't keep plugging it in. And y3 of t turns out to be t squared e to the minus 2t is also a solution. So these are independent solutions. What's the general solution of the differential equation? The form of all solutions written as a linear combination. It's this. Since these are independent solutions, y equals an arbitrary constant times 1 plus an arbitrary constant times the other, the next, plus an arbitrary constant times the last, gives the general solution. There it is. If you like, you can write it in a little shorter form as y equals c3 t squared plus c2t plus c1 all times e to the minus 2t. That's the alternate form. Alright, so there is how you can solve that third degree equation. It's not so bad, right, because it's so like the second order equations that we already did. Here's another one. Suppose I just solve this one, a fourth degree equation. I said I wouldn't take you higher than fourth, but this is the fourth. Fourth derivative plus 4 times the second derivative plus 4 times y equals 0. Well, I know how to solve this because the characteristic polynomials are the fourth plus 4r squared plus 4. Wait a minute, I recognize this. If it was x squared plus 4x plus 4, I could factor it as x plus 2 squared, right? So if I just let x equal r squared, then this is x plus 2 squared, and then x is r squared. So this factors like this, right? Right? If this was x squared plus 4x plus 4, you factor as x plus 2 quantity squared. With x equal r squared, that's how this factors. I'm sorry to repeat that too many times, but what that means is that we have the following solutions. Now we have to solve r squared plus 2 equals 0. Well, r squared plus 2, this is an irreducible quadratic, right? ar squared plus br plus c with b squared minus 4ac is 0 squared minus 4 times 2 times 1 is negative 8 is less than 0. This doesn't factor using real numbers, right? But it factors as r equals plus or minus square root 2 times I. So these are the solutions to r squared plus 2 equals 0, and it occurs twice. So the 4 zeros of this characteristic polynomial are square root 2i, square root 2i, minus square root 2i, and minus square root 2i. Well, we know from our theory of second order equations that e to the, if you think of this as 0 plus I square root 2 and 0 minus I square root 2, that tells you that e to the 0t cosine square root 2t is a solution, right? You take e to the real part, 0 times t, times cosine imaginary part, square root 2 times t. So cosine square root t is a solution by that method that we had. And then similarly also, e to the 0t sine square root 2t, since 0 minus plus or minus square root 2t is a solution. So those are two solutions, but then they repeat. What do we do for the repeated ones? We just multiply each of these by t. So it's the same solutions you got had you gotten 0 plus square root 2I for second order equations, but just two more multiplied by t because you've got those repeated. You can write this succinctly as c1t plus c2 times cosine square root 2t plus c3t plus c4. Oh boy, computer's going to get me here. Hold on. I put it on a timer and I keep on getting interrupted. I didn't think it'd been that long. Apparently I'm talking too long. So I better hurry up the lecture here, huh? It's telling me. All right. And so there is the solution of this one. Let's look at one more. Let's look at a third degree up, let's see, this is the wrong one. Up above. How about this one? d cubed y dt cubed plus 8y equals 0 has characteristic polynomial r cubed plus 8 equals 0. How do we solve that one? Well, there's a few different ways. One way is just put r cubed equals minus 8. And what are the cube roots of negative 8? You can figure that out with a nice diagram. If you do it in polar coordinates, so r, the polar radius, I use capital R instead of little r, e to the I theta. If I use that for my little r here, so I write the number little r, which could be a complex number, in its polar form, r e to the I theta. And then r cubed is this cubed equals negative 8. Remember this is a long ago algebra thing, but if you have a complex number in its polar form to a power equals a number, you can rewrite this as r cubed e to the I theta cubed, or r cubed e to the I 3 theta cubed equals negative 8, which is expressible in polar form as 2 cubed for 8, and then minus 1 is e to the I pi, and then you can add any multiple 2k pi, and it still gives you minus 1. So these are all the ways that a complex number in its polar form, r cubed e to the I 3 theta, that's the polar form of little r cubed, can equal negative 1. These are all the expressions for negative 1. So k can be 0 plus or minus 1 plus or minus 2, and this is always a solution. All right. Well, what does that mean? The idea is that r, capital R is the polar radius, so it's a real number. R cubed equals 2 cubed means that r must be 2. And e to the I 3 theta equals e to the I pi plus 2k pi means that theta is pi plus 2k pi over 3, where k be any number. Well, if you figure this out, even though this is an infinite number of cases, only 3 of them, k equals 0, 1, and 2, give distinct results. After that, these all repeat. In other words, when you put in those other values of theta and calculate r e to the I theta, you get the same complex number after k equals 2. So you plug in k equals 0, and you get, let's see if we can maybe move up just a little here. You plug in k equals 0, and you get 2e to the, well, let's see. Theta had to be this. When you plug in k equals 0, you get r equals 2 and theta equals pi over 3. And you calculate the standard form of that complex number. 2, remember, e to the I theta over, these are the three numbers. That you get out of here. So r is 2, and theta is pi plus 2k pi over 3. And then you write the complex numbers as r e to the I theta with this theta and this r, and you calculate what they are. remember e to the I times that number is cosine times that number plus I sine times that number. If you put in k equals 0, so it's just e to the I pi over 3, you get, this is cosine pi over 3 plus I sine pi over 3, all multiplied by 2. If you put in k equals 1, then this becomes 2 pi plus pi over 3 becomes 3 pi over 3 is pi, and so you get twice cosine e to the I pi is cosine pi plus I sine pi by Euler's formula. And then if you put in k equals 2, you get pi plus 4 pi, let's see, pi plus 4 pi is 5 pi over 3. Let's see. Apparently I didn't write that one down here. But you get 2 times cosine 5 pi over 3 plus I sine 5 pi over 3. And that one, if you find its standard form, it comes out to be 1 minus I square root 3. This one, cosine pi over 3 is a half, and sine pi over 3 is square root 3 over 2. All multiplied by 2 gives you 1 plus square root 3 times pi. So this one, right, just putting in square root 3 over 2 for this and a half for this. I'm sorry, half for this and square root 3 over 2 for this. All multiplied by 2 gives you 1 plus I square root 3. The one I didn't write on here, twice cosine 5 pi over 3 plus I sine 5 pi over 3 gives you this one. And this one, cosine of pi is 1 and sine of pi is 0, so you get, cosine pi is negative 1, this one's 0, so you get negative 2 here. And so 3 independent solutions come from these. Again, from these two solutions, you get e to the 1t times cosine square root 3t and e to the 1t sine square root 3t. That comes from these two complex conjugate values of r. And then from negative 2, you get e to the minus 2t as a solution. And you take an arbitrary linear combination of those three, c1 times 1 plus c2 times another plus c3 times another. And that gives you the general solution of the differential equation. So it's a nice abstraction of what we did before. You just have to be able to solve higher degree polynomial equations and figure out to multiply by higher powers of t for the general solution. Here's some homework problems to try.